Before introducing our keynote speakers, some words of thanks. First, thank you to the person who makes this event possible. Although the individual prefers to remain anonymous, we are grateful for inspired philanthropy. The symposium honors our donor in that it weaves together the threads of a strategic philanthropic program that benefits higher education, the scientific research community, libraries, and a sustainable future through the preservation and restoration of green space and biodiversity. We are grateful for the generosity of the scholars who have come from all over the country to share their research and collective wisdom, to experts from the local community who are taking time to attend this symposium, to August Froelich of the Nature Conservancy and Joe Kuntz, Biology Department Chair, who assist in planning this event, to the people who are participating in the symposium demonstrations and poster sessions, and a special thanks to Gina Midlick for her superb project management skills and hard work. Each year we've held the symposium, Joe Kuntz reminds us at the planning outset that there's a critical role for libraries in any research using GIS technologies. Who else, he always asks, will provide easy and open data access, foster use through tools and training, and curate the data? In thinking about who might best respond to those questions, one person came to mind, a person with a breadth of knowledge and an ability to synthesize and make understandable complex topics, who literally travels the world describing the potential and promoting strategies for networked information and service development, Cliff Lynch. Clifford Lynch has been the director of the Coalition for Networked Information since 1997. CNI, jointly sponsored by the Association of Research Libraries and EDUCAUSE, includes 200 member organizations concerned with the use of information technology and networked information to enhance scholarship and intellectual productivity. Prior to joining CNI, Cliff spent 18 years at the University of California, Berkeley Office of the President, the last 10 as Director of Library Automation. He holds a PhD in computer science from the University of California, Berkeley, and is an adjunct professor at Berkeley School of Information. He is a past president of the American Society for Information Science and a fellow of the American Association for the Advancement of Science and the National Information Standards Organization. Cliff Lynch is a prolific author. He currently serves on the National Digital Strategy Advisory Board for the Library of Congress, Microsoft's Technical Computing Science Advisory Board, and the board of the New Media Consortia. Please join me in welcoming Cliff Lynch.
I'm very pleased to be able to be here, and I'm looking forward to learning a lot from the presentations that we've got scheduled. My opening talk is going to try and frame some of this in terms of some broader developments that are going on in science funding, and in rethinking at some level some of the roles and responsibilities of various organizations in managing the record of science. I'm going to focus a bit on science, but as I'll get into a little more shortly, much of what I'm going to say really has applicability far beyond the sort of traditional physical and life sciences and into social science, into the humanities. I think that that's going to be a rich theme for us to think about as we go forward, because GIS really has that same character of really running across from the hard sciences to the most fundamental humanities in its interests. Spatial organization is critical to all of those areas as an underpinning. Now, I'm going to start by talking about eScience and cyberinfrastructure and a set of related developments. And I have to say that I've been struck as I've been preparing my comments here about how some of the rhetoric which one sees around, for example, Escience and e-research today actually echoes rhetoric that one sees about GIS 20, 30 years ago as a sort of an integrative force, a force and a framework that lets interdisciplinary and multidisciplinary work move forward in a way it wasn't able to before. It really is interesting to me how GIS as a discipline and as a set of practices that have moved into a vast array of scholarly disciplines has kind of trailblazed for a lot of what this broader set of information technologies that operates under the banner of e-science and e-research are now trying to do at greater scale. As a kind of a reflection on how many disciplines now are engaging GIS in a basic way, just look at the diversity of speakers here. Just, you know, go through the affiliation, the departmental and disciplinary affiliations, and you begin to get some, you know, sense of that. So let me begin with some comments about e-science and e-research. In many different parts of the world, there was a realization which mostly started in the late 1990s that something pretty fundamental was starting to change in the practice of many kinds of science. And that set of changes were triggered by a whole bunch of underlying developments in information technology, specifically very high performance networking that was increasingly ubiquitous, the ability to use those networks to get at very high performance computational resources in order to do simulation, to do analysis, to do visualization. The ability to store and access very, very large shared databases and data sets through these networks. The ability to attach instrumentation to the network, to use the network both as a way of funneling in observations from increasingly sophisticated sensor networks, and also the ability to share high-end experimental or observational apparatus, you know, things like particle accelerators, space telescopes, this sort of thing. Finally, the ability to use the network to support modes of collaboration that we had been unable to support well in the past. Collaborations across geographically disparate organizations. It's interesting that the early language they talked about there was a language that stressed ideas about collaboration. For example, harking back to Bill Wolf's coinage of the term collaboratory in the 1980s and the ability to establish such things on the network. Nowadays, what they mostly talk about, which I think is a very helpful reframing of this, is virtual organizations. The notion that you ought to be able to, in a fairly lightweight fashion, gather up a group of people without too much regard for their home institutional affiliations in order to tackle a problem, in order to analyze a set of observational data, in order to build something or pursue some kind of scientific or scholarly objective. And in an equally lightweight fashion, when the given virtual organization has fulfilled its mission and outlived its usefulness, close it down and move on to the next thing, hopefully in a sufficiently orderly fashion that the records and the outputs and the products of that virtual organization are preserved in some kind of coherent fashion. So that collection of things, high-performance computing, observational and sensor systems attached to the network, large databases, virtual organizations, those became the core of a set of ideas which in Europe they referred to as eScience. So for example, by 1999 or thereabouts, the UK had a sizable eScience program running. The European Union had various eScience initiatives folded into the 6th framework. In Asia, they often referred to it as cyber science rather than eScience. I don't know why. In the United States, in the interest of being as perverse as possible, rather than talking about what we're doing, eScience, we use the code, or at least many of us use the code phrase cyberinfrastructure in order to refer to these kind of developments. And that comes mostly out of the National Science Foundation. There was a very influential report that was finally issued in 2003 that was authored by a committee chaired by Dan Atkins, who was then at the University of Michigan. That report started life as one of the sort of once a decade looks that NSF does at what it should be doing about high performance computing as part of the infrastructure that it helps to support for science and engineering in the United States. And Dan Atkins and his committee very quickly realized that you really couldn't just talk about high performance computing in isolation anymore. You had to really factor in the broader set of influences that I just described. And when you did that, you came up with an agenda for investing in what that committee termed cyber infrastructure as a way of really fundamentally changing the practices of scientific and engineering research. And they developed a very elaborate plan in there, which has moved on to implementation within the National Science Foundation. There is now an Office of Cyber Infrastructure there, reporting directly to the Office of the Director of the National Science Foundation. Dan actually went on leave from the University of Michigan and is just completing a tour as the director of that office, and will go back to Michigan in, I think, June or thereabouts. I will say a couple of things specifically about what that office has been doing in a few minutes. The basic ideas of cyber infrastructure or eScience or whatever you'd like to call it, I think should be evident to most of you as playing out in many, many different scientific developments, ranging from the virtual observatories that are showing up in astronomy to the various databases in molecular biology, the work that's going on in earth sciences and ecology, in species diversity. There's applications of this almost everywhere you look. I mean, there are a few, sort of holdout disciplines where I would say the influence is relatively limited, but certainly this is happening on a very large scale. Now, The National Institutes of Health have also begun to factor in a lot of this thinking in their plans going forward. They don't, to the best of my knowledge, have a specific agenda that goes under the title Cyberinfrastructure, but rather have integrated it into their broader multi-year plans. And there are certain agencies within NIH, notably the National Center for Biotechnology Information at the National Library of Medicine, that have been very active indeed in many different aspects of the agenda around advancing cyber infrastructure. Now, I want to spend a fair amount of time on the data-related areas, but before I go there, I just want to make a couple of quick comments about some of the other areas, particularly as they connect to GIS. One is the whole broad area of simulation. It's really quite remarkable what's happened here, and the extent to which simulation is now becoming a fundamental tool, which more and more people are starting to argue needs to be taught to, undergraduates on a very broad basis across a considerable range of disciplines. This is very closely coupled to geography. Often one wants to run these kinds of agent-based simulations now, and you want to run them in the context of specific physical systems, urban systems, transportation systems. It's actually kind of astounding how much work has gone on in this area and the degree of precision that seems to be possible. For example, I have seen now for at least 3 or 4 years rather high resolution simulations that do things that look at disaster planning, for example, for a geographic area, but they do that based on a lot of data about things like, what does the morning commute look like? And what does the morning commute look like when there's an accident on this bridge? And what does the morning commute look like during spring break? This is actually a pretty remarkable thing to be able to work. And one of the challenges that I think we have now is how to make more of these simulations interoperate with each other to be able to use data from other sources. I'll give you one other example of these kind of simulations, which I came across about a year ago. There's a group that is based largely at the University of Chicago that's basically doing simulations of early agrarian society, where you simulate it household by household, agent-based simulations here, and you try out certain kinds of social assumptions, like, do households band together to bring in crops? So during planting and harvesting season, does the village work as a village, or does each household work its individual collections of crops? And then you can plug in real data about what did the weather cycles look like for 300 years there. Was it very dry? Did they have droughts? Did they have floods? And you can actually go through and sort of simulate whether these societies fall apart or thrive or overpopulate. This is this is absolutely remarkable stuff that nobody would have tried, I think, 20 or 30 years ago at this level of detail, and which is now, at least computationally, getting within reach of almost anybody with a yen to do it. The bigger sorts of things I'm talking about, simulating Seattle, or doing very detailed simulations of entire nations or international conflicts, is still very much on the high end of computation. But I do think that that collection of developments is very important and connects up here. The other thing I want to say a word about is sensors. There are astounding things going on, as I know many of you know, with sensors. And this is getting to be a very confusing area. It's confusing because we're doing a bunch of different things at once here. One collection of things we're doing is we're building new sensor technologies. So, for example, many of you have probably seen some of these research programs that are intended to develop what they call smart dust. Very, very tiny, very, very cheap radio-based sensors. You just toss them around like dust, and they automatically build up networks and do the right sorts of things and collect data of various kinds on things that you might be interested in. They're much more sophisticated kinds of sensors starting to go online as well. One of the interesting things I've seen in this area is the kind of thing that people who are interested in ecology and biodiversity are starting to deploy in a few places. What you do here is you lay out a substrate of fairly cheap, fairly stupid sensors that are connected up either by radio, or if you're on the seabed, maybe you do it with fiber optic. But you know, they can sense a few things. They can sense, mostly what they can sense is conditions that they think might be anomalous and might merit further attention from something smarter. So you then overlay these kinds of dumb sensors with some smarter sensors that can move. They're more expensive, they're bigger, they can have a bigger power budget because one of the places they can move is back to where they can recharge their batteries. But you overlay this sort of system of mobile sensors on top of here. Now you've got a sort of an active sensor network that's really terribly different than the kind of passive deploy sensor networks that we're talking about in the past. Okay, so you have all those kinds of developments in the research community. But then you have another set of social developments. Basically, you know, we're kind of censoring our society in a million different ways. Everything from smart highways to putting closed-circuit TVs everywhere, TV cameras everywhere, and attempting to couple them to various sorts of recognition software. Cell phones. Cell phones actually are sort of sensors at this point. They kind of know where you are, the more recent ones. They're going to get better at it. There have actually been proposals to put other kinds of sensors in cell phones, you know, radioactivity sensors, for example. All of a sudden, if you mandated the inclusion of these things in cell phones, you could very rapidly deploy a large national sensor network for this or that. And it comes with a telecommunications system to get the reportage back to where it needs to go. Kind of an interesting prospect. Now, I don't want to necessarily suggest that that's a brilliant idea. There are a lot of problems with it, but I think it just is kind of indicative of the scale at which we're starting to deploy various kinds of sensors around the place today, which can also feed into simulation, can also feed into observational databases, can also be used to validate modeling, all sorts of interesting properties. I cannot resist mentioning just one or two other quick things about sensors. We've moved a great deal of social, commercial, and societal activity to the internet. And the internet is itself a giant sort of sensor and vacuum cleaner of a sort that we've really not had much experience with in the past. In fact, you know, you're starting to see social scientists and political scientists and government people and all sorts of folks building special purpose sensors, and that's really what they are, on top of the internet, that look for traffic patterns. They look for certain kinds of language at certain sites and things like that, and they trigger activities based on it. So we need to recognize that in the form of the internet, we have an enormous sort of social sensor network of a kind that we've really never had before. And then the last thing I'll say before I get off this topic and onto data is this. As it happens, I've had some conversations with researchers at most of the major internet companies over the past 18 months or so, places like Google and Yahoo and Microsoft. And you know, for all you might think they don't, these companies internally are fairly vicious about preserving the privacy of their user data for good business reasons. They don't basically, you know, sort of let their researchers shop in personalized data and pass it around the way you might think in your worst nightmares. Yet, all of these folks have said to me, basically, I could not do the kind of research that I'm doing right now, looking at large-scale, anonymized kind of internet trails at a university, because I couldn't get it through human subjects. Just something to think about there. We've built these tremendous data sources, and we've built a system that I think was originally designed for all the most noble of reasons, which now is starting to have some effects that we may want to think about. Okay, let me move on, and let me spend the rest of my time pretty much talking about the data side of cyber infrastructure. One of the things that I think was really, really significant about the Atkins report in particular was the extent to which it recognized data, observational data, simulation data, field collected data, databases of various kinds as a fundamental cornerstone of e-science and e-research. Before that, certainly folks like the UK programs had given, you know, some space to data, but it had tended to be a little bit of a stepchild to the high-end networking, high-end computation, data collection. The NSF report, which is complemented by a report on long-lived data sets, which went in, I think it was 2004, to the National Science Board in the US and was approved there, really deals with the whole complex of questions about data and what the role of data is in cyber infrastructure. It points out that there is a need for an organized process, not simply of data preservation, but of data curation. And I'll get into a little bit of the specifics of what data curation is taken to mean by various communities in a moment. It stresses the notion that you're not keeping data just because it's fun or it makes you a better person or something, but really so that we can revisit it in future, perhaps in contexts that are very different and very distinct from the contexts in which it was originally created and analyzed, in order to do new scholarship. In other words, the whole point of maintaining these data resources is not just about creating archives for the sake of archives by and large, but for enabling downstream additional kinds of research and discovery. Now, I need to, mitigate that a little bit. There are situations where you need to keep data for various kinds of social reasons. For example, you might keep it in a clinical trial as long as the people who were involved in the trial were alive, because you might need to go back to those records. If you are doing things like burying toxic waste that has a long lifespan, you would probably do well to maintain the records of where you buried that at least as long as the expected lifespan of the toxic waste, and probably it would be a good idea to keep it longer because we don't always get our lifespan guesses right. If you're doing construction, public works, obviously you want to keep the records of what you've built for as long as what you've built is out there. So there certainly are a wide range of commercial, governmental, and social situations where you need to keep data for its kind of inherent purposes. Here, the attempt is to think beyond this and recognize just how hard this is to do. There's certain kinds of data which you can kind of reasonably assume you're going to reuse in various ways. For example, think about the notion of doing meta-analysis across multiple clinical trials. There's a certain commonality in the data, but the really hard ones here are the places where you want to take data that, who would have thought you could interpret it that way? And interpret it that way. Maybe years later, very far from the source. Maybe you're using information about fishery yields to make inferences about weather patterns, or you're using weather pattern data to make inferences about how much people were getting to eat in a certain society at a certain time. These are things that are pretty far removed and that take a certain amount of creative insight that is, one of the fundamental drivers of really successful, exciting, multidisciplinary scholarship to recognize. How do you do this on a systematic fashion? Let's remember that it costs money to preserve data. We don't want to preserve everything. In fact, we can't preserve everything. Interestingly, it turns out there's still a very, very strong bias among most of the scientific funding organizations, to preserve as little as possible. Their nightmare is that they get caught in a situation where, as time goes on, more and more of their funding that they would like to use to support new science or new scholarly work is basically already spoken for in terms of supporting infrastructure, be it instrumentation or be it data sets. And the data sets, of course, are the worst because instrumentation typically has a pretty short lifespan of 10 or 20 years, and then it goes away, and you can have the discussion about what new instrumentation to build. Digital data sets have this sort of forever quality in the nightmare scenario. One could imagine, over a period of 50 years, the entire science budget being siphoned away from doing science to preserving the records of old science. We don't want to do that. So we're faced with a whole series of very hard questions about what do we keep, what don't we keep, what's gone forever if we get rid of it, what can we recreate it a certain cost and therefore do some kind of trade-off about, well, if we need it again, we could build the piece of observational gear again and recapture the data. We're just beginning to get a language, really, to talk about these kinds of things. And this takes me into this set of questions about data curation and about roles and responsibilities for data. The National Science Foundation reports have coined some kind of interesting terminology. They speak of data curation, and they speak of a breed of people that they term data scientists. And it's not exactly clear where data scientists come from. Right now, there are a couple of programs scattered around at some of the schools of information in the United States that are starting to talk about data science programs. For example, Illinois Champaign-Urbana is starting to do something in this area. But we're a long way from having, particularly outside of the narrow and somewhat specialized tradition of biomedical informatics, armies of data scientists coming to solve our problems. So right now, everybody's kind of dealing with this catch as catch can, kind of an interesting mixture of disciplinary people who've become interested in these issues, information technology or library people who've become interested in these issues, often people wearing sort of a funny, multidisciplinary background coming to these. We've got some problems of scale, too. Somehow, I don't think it's going to work to say that the answer to this is to produce a set of people with a PhD or an MD in a disciplinary science, and then a second PhD in information science. If you start thinking about the costs of training a large cadre of people with those kinds of qualifications, I think it's probably not hard to conclude that this is going to get unsustainable fast. You can afford to do that if you're the Large Hadron Collider at CERN and you've got 8,000 physicists signed up and an army of information technologists. You can also afford a curation department. The problem is the smaller the project gets, the more difficult it's going to be to support this. Curation involves making sure that you've got the data packaged up accurately, you're preserving its integrity in some fundamental way, that it is documented as to its context, it's described, you've got enough description to make sense out of it, and that's a startlingly hard thing to do in some areas. It actually starts to reach very deeply into disciplinary culture and disciplinary practice and the amount of commonality in disciplinary practice. It is very interesting that if you talk to physicists, for example, they'll often say that this is fundamentally unmanageable over long periods of time in high energy physics because it is so tied up in the design of the detectors in their experimental apparatus. They would, in essence, have to rebuild the detectors, rebuild the experimental apparatus to be able to make sense of that data 50 years downstream. There's a very interesting project that the NSF funds in earthquake engineering. They build these things, I don't know how many of you have seen them, called shake tables. Some of them are very big. So you build like a model city or a model bridge or something on this shake table, and then you shake it, like they're, with these big hydraulic things, like it's having an earthquake, and you instrument this. And these are very expensive. I mean, they're expensive enough that there are only a couple of them in the country. And they're actually on the net at this point. So you've got groups, for example, at Buffalo, and you've got another group out in California. And they run experiments on these things where they collect a ton of data readings. Now, they'd like to be able to preserve and exchange this sort of data. But it turns out that in order to really capture it, they have to capture a tremendous amount of context about the experiment in order for it to really be meaningfully reusable. Now, you know, at the other end of things, if you are nailing down a crystal structure for a protein, the context is typically a lot more constrained. There's a group of people who take who are interested in computing or observing the structure of proteins, and they've been doing that for a long time. And it's a sort of a better constrained problem. So we face all of these kinds of issues in data curation. Once you've got the package kind of gathered up, it then needs to go someplace for preservation for as long as it needs to be preserved, and presumably there needs to be some process for deciding when you don't need to preserve it anymore, as I indicated earlier. And some entity needs to be responsible for running that process. Now, there are some very interesting discussions going on right now about where the locus of responsibility should reside for managing this kind of data. On the one hand, it's increasingly part of the fundamental documentation of scientific process and scientific results. It's intimately linked, in many cases, with the traditional journal articles that have been used in order to announce and share those results. And you're actually seeing several different models evolve now. You are seeing one model that basically uses a disciplinary repository. And you see this in molecular biology, for example, where the presumption is if you're going to write about a sequence, it goes in GenBank, you get an accession number for it, you cite the accession number in your article. And basically, most of the leading journals won't publish an article like that unless you have got an accession number that indicates that you have deposited your data. So actually, they have both, through editorial practice, which reflects a kind of a community consensus, that they've both sort of set up a management model, and they've also set up some norms for when that data is shared. And of course, data sharing norms vary dramatically from discipline to discipline, ranging from the humanities, where you may pass it on to your graduate student with an oath of secrecy, all the way through some of the private funders now who are funding research on various diseases and are actually demanding pre-publication data sharing by the people they fund, because they feel that that will expedite the processes of discovering cures and treatments for the diseases that they're in business to try and find cures and treatments for. Anyway, so one model is this sort of disciplinary repository model, and the problem with that model is that somebody needs to pay for the disciplinary repository. Either they've got to be underwritten as a public good. Think of organizations like the National Center for Biotechnology Information at the National Library of Medicine. Think about some of the other similar kinds of data banks that have been set up, the protein data bank. Second model, a few journals are saying, well, we'll take it. Actually, we will think of scientific articles in a broader way. And we will say, give us the article, give us the data, give us the programs, things like that. Give us the whole package. And in fact, some journals are starting to get a little more aggressive about this. There have been some very embarrassing scientific misconduct situations recently, which have taken some of the really leading journals to the point where they're encouraging their referees, where they seem to feel it's necessary, to actually demand data or try and arrange replication of a result prior to publication in some cases. But as far as the publication proper, typically you would see these data sets as what some of the journals call supplemental materials. The problem here is often the journals are a little vague about who really has the long-term preservation commitment for the supplemental materials. They'll say, yeah, the text of your article, we'll take responsibility for that, but supplemental material, best effort maybe, or until we feel like doing something else. They also are a little weaselly sometimes about how much supplemental material you can give them. Spreadsheet, fine. 2 terabytes of sensor data, nah, too big, we don't want to pay for that. So the journals have been really iffy about this. The third player, the sort of player of last resort that's starting to emerge slowly and painfully, is the universities themselves that host most of this research. Typically through the mechanism of although not always, but typically through the mechanism of the university library as a place where you can deposit this. And what you do again is you'd give a citation to the local repository where you'd put the data. Now, there's some huge financial issues around this. Typically, universities through their libraries have taken responsibility for managing most of the scientific record in the form of journal subscriptions, primarily. There is a national library that deals with medicine and the life sciences in the US. The Library of Congress is not exactly a national library, and its collecting policies skew heavily to areas around culture and history as opposed to science and engineering in recent decades, leaving that mainly to the university community. Taking stewardship for data of this kind is a very significant expansion of role and investment for our universities. It also has got some scaling properties that are unattractive and need some thinking about. For example, we probably don't need 40 universities with centers of expertise in data pertaining to classical languages. We could probably do with 2 or 3 and some arrangement that says the other universities will contract out a certain amount of the service there, so that basically as you scale it up, you spread disciplinary specialization across universities in some kind of strategic way that hopefully is at least somewhat aligned with strength of academic program and focuses of strategic academic interest. So that's kind of how that scene is beginning to play out in terms of data curation responsibility and roles. And this is a big deal because more and more of the scholarly work has at least parts of its output now in data sets, in material that's visualized, in image collections, in things that are very different from the sort of classical published books and articles that have always represented the output of scholarship. Now, I want to just conclude with two last observations to give you a little additional perspective on this, and then I will open this up for some discussion. The first, I said I'd focus mostly on science, and you've probably caught me occasionally using the term e-research rather than e-science. E-research being the politically correct term, because in fact, if you think about all the things I talked about how the scientific process is changing with these infusions of technology, I think you will find that you can identify very similar changes, although much less evenly distributed, among the social sciences and the humanities. If you're interested in this topic, I'd invite you to have a look at a report that the American Council of Learned Societies commissioned, which came out in 2006, late 2006, which looks specifically at the question of cyber infrastructure for the humanities and the non-quantitative social sciences. It was deliberately designed as a sort of a complementary report to the report that Dan Atkins and his committee wrote for the National Science Foundation. And they make some very striking arguments about parallelism. They identify lots of innovative projects in the humanities. The folks in the humanities, of course, are never shy about thinking big. They suggest that amongst the infrastructure components they'd like are comprehensive digital libraries representing the writings, spoken words, performances, and images of all human culture from all times and places. So they'll start there and then move on to manipulating tools. Science mostly just wants, we'll just take the scientific literature and all the observational data sets we can get back to day one if we can find them. It's a much more constrained sort of a thing. So I would be very mindful of the implications of this in the humanities. The other point I want to make, again, it's a point of putting this in perspective, is that if you talk to the science agencies about cyber infrastructure, they will tend to trot out this set of marquee projects, the Large Hadron Collider at CERN, various large-scale biodiversity initiatives, efforts to survey the Pacific Ocean floor. And there are a couple dozen of these that are all very, very big, many millions of dollars, multiple institution, large science projects. And these are, sort of wonderful case studies of how these technologies can make the difference. But if you really go deeper into the data, if you look at various studies that have been done at an institutional level, if you look at this study from the ACLS, what you find is that scholarly practice isn't just changing at the level of these marquee projects. It's changing at the level of, a lab with a principal investigator and 2 doctoral students that he or she is funding. It's changing at the level of a faculty member in the humanities who doesn't even get grants like you do in the sciences. If he or she gets a grant, it's to go to Europe for a semester to poke around in an archive or write a book. All of these folks, this is starting to move very, very deeply into disciplinary practice, very widely. All of these folks are starting to depend on and generate significant digital data collections to practice elements of e-science or e-research in their scholarly work. And all of them are going to need to be supported by the systems which we devise to curate, preserve, manage, and facilitate the reuse of data sets. So I hope it's been an interesting tour. We've stopped at a lot of places. There are lots more places we could stop at, but I think what I'd like to do at this point is to take a pause and to invite questions, comments, or observations from you. Sir.
Do you see any future in product liability for information?
Oh yes, that's getting to be a very touchy area. I mean, I guess maybe before I give you my take on that, could you say a little more about what you mean by product liability for information?
Someone puts in a faulty data set or faulty set of predictors that results in catastrophes or loss of economic livelihood, and maybe those people put together those data sets be sued.
Mm-hmm. Yeah, I mean, I think there's a lot of issues around that right now. We're starting to see a whole set of them emerge around pharmaceutical trials, about whether data was suppressed or distributed, and who got to see it or didn't and why. I think that there is a lot of pressure from lawyers generally to get rid of old records because they are nothing but liability. I mean, that's the sort of general wisdom in most large corporations now. You have a retention schedule for your records and data, which is driven by a series of business and regulatory processes. And as a general rule, you don't want to keep anything one day more than you have to, because at that point, it's just pure liability waiting to happen. I don't know how we square that entirely. One of the questions that I'm starting to hear show up in several contexts is about peer review of data and about whether we can have meaningful peer review of data and what that should mean. Journals are getting pretty squirrely now about this question of when they peer review something, exactly what are they peer reviewing? Is it the article? Is it the result described in the article? Is it the article plus the supplementary data, or the data that's been deposited in, GenBank or wherever it is? That's going to show up as an issue. People are interested in peer review of data also for tenure and promotion purposes, as they spend more and more time building up data sets rather than writing up traditional papers in some areas. So I think there are a lot of tricky questions there. Another thing that's emerging is the notion of databases that are edited in the same way that someone might have traditionally edited an encyclopedia, where you get a group of editors and an editorial board, and their intention is to construct something that on a continuing basis reflects the kind of best consensus state of knowledge in a given field. And that kind of editorial process begins to give you some protection from that, in the sense that at least there's a relatively open process of revision and scrutiny. But the short answer is yes, I think this is a problem and it's going to get worse.
I just want to point out the important role of the NASA Data Acquisition Center, the DACs, and particularly CDAC, the Socioeconomic Data Acquisition Center, which addresses somewhat the scarcity of data and accessibility of data to the humanities, which is a big problem. So I recommend to all of you to visit the website of CDAC, SEDAC, because they also have dealt with a lot of the issues about data, data acquisition, data distribution, etc. I do have one question, because in one of the working groups meeting of the center, Michael Goodchild stated, and I use that sentence a lot, we really should not worry at all anymore about storage of data. That should not be an issue at all. Mm-hmm. And in a way, this may have to be revisited, and particularly the data may be stored, but how accessible are they? So if you want to talk a little bit about that.
Oh, that's a great question. I've heard Mike say that a few times too. I guess, let me say 2 or 3 things about this. Right now, the price of data storage is going down fairly rapidly. And I think there are good reasons to think, for a while at least, it will continue to do so. What that means is that for most data, storing it, the sort of raw costs of storing it are not really very significant. And particularly if you could afford to store it for 5 years, you can afford to store it forever, because within 5 years, the prices will have fallen and the sort of scale of data versus cost will be down to a manageable level. You can see this graphically in data produced by human beings. For humanists, or for people concerned with data produced by humans, particularly things like spoken data or written data, or even getting close on video, this is just not a problem. People don't write that fast, they don't talk that fast. Saving every word you ever wrote or spoke, just not that big a deal. And so this is what's going to start to happen. Getting rid of words that people write or things that people speak is going to be done for other social purposes, not for saving money. It may be done because we want the ability to alienate bits of our activity or history from ourselves and everyone else, to forget, but not to save storage space. And the implications of this, by the way, for people like historians are going to get really interesting, because you're already at the stage where if you're doing certain kinds of history, you no longer have enough hours in your life to review the relevant documentary evidence. So you're now, history takes on a data mining element in the same way that large-scale corporate litigation in the age of things like Enron takes on a data mining element. There's just too much stuff for people to read in the time frame. It's very interesting to look at what the National Archives does with government computers. When they have a change of government, what happens is that people go into places like the White House and they take all of the hard drives out of all of the machines in there, and they ship them off in big boxes to the National Archives. And the National Archives basically has written some software that throws away all the duplicate copies of Windows and then just kind of amasses all the other files. And this is just, it's a non-storage problem, you know. Now, having said that, there are always some scientists who are interested in pushing the highest degree of resolution they can get through their sensors. Often, because of the way sensors work, the data stream actually goes as the square or the cube of progress on the sensors. You know, they're not happy unless they're pushing the state of the art, and more specifically, any budget they can lay their hands on. There is a class of data in there that I think is a problem, but I think it's a relatively small one.
Yeah, you mentioned GenMed and the role of journals in enforcing the accession number policy. So you have an accession number associated with a sequence. Do you see going forward that same procedure occurring for better metadata associated with sequences, or is there another way to get metadata quality up?
I suspect that the metadata improvement will come through some other source, and I need to say, I'm not an expert in this area, but I think that they probably want to keep the deposit stuff as streamlined as possible, and probably would prefer to manage the metadata elsewhere than as part of that deposit. The other piece of that is some of those deposits are very time critical and very competitive. So people don't want to be slowed down messing around with metadata there. Thank you all very much.